Hello, welcome to Flipped. Today we are on the empirical formula of compounds, and it's obtained after conducting an experiment. It's the formula that we get from our data. So in exam questions, they will hint to you that, oh, this data is gotten from after doing an experiment. So you must immediately link it to empirical formula. Empirical formula is a simplified ratio of elements. Okay, it's not necessarily the actual molecular formula. For example, from our data, we know that the ratio of A is to B is 1:1. What does it mean? It means that for every one A atom, there's one B atom. Okay, that's just simply it. And the empirical formula is written as AB, okay, which is just A1, B1. Okay, for every one A atom, there's one B atom. But we don't write the 1 because for ones, we don't write the subscript. But in actual fact, the molecular formula can be A2, B2, A3, B3, or whatever, AN, BN, etc. Okay, so this is molecular formula. But this is, this one, A1, B1, I mean AB, is just the empirical formula, which is just a ratio. Okay, you can multiply by whatever number to get the actual molecular formula. Okay, let's start off with the empirical formula first. Okay, so this one, an oxide of iron contains 70% iron. What is the empirical formula of this oxide? Given that the relative atomic mass for Fe, iron, is 56, O is 16. This can be obtained in the periodic table as well. So first step is to write down the mass or percentage of elements. We can see that they have given us percentage and not mass. Okay, so just write this down. Iron is 70%. Let's write it down together. Okay, whereas for oxygen is, what do you think? Okay, 30%. Because in oxides of iron, there's only oxygen and iron. A hint they give you, okay, is actually just given here. Fe and O. They did not give you anything else, so you can be in some sense they are hinting you that, oh, in oxide there's only Fe and O. Okay, next step is to divide by Ar, which is the atomic relative atomic mass. So 70, we just plug it here, divided by 56, am I right? To give us 1.25. Whereas for O is 30 over 16 here, to give us 1.875. Okay, step 3 is to divide the number, divide whatever number you have with the smallest number in step 2. So there's only two elements here. We compare which one is smaller. Okay, so it's 1.25 being the smaller one. So first step, we just take 1.25 divide by itself, 1.25, because it's the smallest, to give us 1, correct? This one, 1.875 divided by the smallest number, 125, to give us 1.5. Okay, but we cannot, so this one, okay, you might think, oh, it's the ratio, correct? Which is not wrong. For every one Fe atom, there's 1.5 oxygen atom. But in our molecular formula, okay, empirical and molecular formula, we don't write decimals. So it has to be a whole number. Okay, so the next step is to multiply such that the number in step 3, it forms a whole number. Okay, so what's the closest one that we can get? 1.5, the closest one we can times 2. Okay, so 1.5 times 2 to give us 3. Whereas this guy must times 2 as well to give us 2. Okay, so you realize that I must multiply and divide by whatever they are the same thing. Okay, for example, 2 here, and 1.5 here, and 1.5 here. Okay, so whatever I do to the left hand side, I must do to the right hand side, except for step 2. Okay, because this is their individual relative atomic mass. Okay, so once we get this, we can see that for every 2 Fe atom, iron atom, we need 3 oxygen atom. Okay, and so the ratio of Fe is to O is just 2:3. Makes sense, right? The number we just plug it from here. So now my empirical formula, I can safely say is Fe2O3. Okay, this is a subscript. That means it's written at the bottom instead of on the same line with Fe and O. Okay, so Fe subscript 2, O subscript 3. This is our empirical formula. So this is not the end. Okay, we still have one more thing to cover, which is called the molecular formula. So molecular formula of compound, it's why do we need this? Is because empirical formula does not give sufficient information, so we need this. Okay, because obtaining a ratio is not enough basically. Okay, so molecular formula is always a multiple of EF is empirical formula, and that's why we can see that MF, which is molecular formula, is n times of EF. Okay, so let's take the AB example just now. So my empirical formula I found out is AB. Okay, so I times 2 to get A2B2, or I can times 3 to get A3B3, or I can times n to get ANBN. Okay, so with this, you can see that to get n, this is the formula that we require. N equals to molecular formula of MF divided by molecular formula of EF. Okay, I think it's easier to illustrate this with an example, so let's just jump straight into it. Okay, this is our question. Unknown substance contains 3.6 grams of carbon, 0.6 grams of hydrogen, 4.8 grams of oxygen. Okay, given that MR of this MR of molecular formula, okay, is 180. So this is the actual molecular formula. It has 180 number, 180. Find out the molecular formula itself. So this one, the first 3 steps, okay, are the same as what we have done for empirical formula, except that we skip step 4, which I can show you. It's this one, okay, because went ahead and solved it. Okay, so it will form a whole number, so we don't have to multiply a number that forms a whole number. Okay, so we can skip step 4 here. Okay, but it's always good to keep that step in mind in case you need it. Okay, but anyway, back to this. The mass of remember the first step is to either write the mass or percentage. Previous example, they give us percentage, so now they give us mass. Okay, so we just write in the mass. So the mass of carbon in this case is 3.6 grams, right? It's just here, so I just write it here, 3.6. For hydrogen, it's 0.6, it's also here. Oxygen, 4.8, also here. Okay, so I just write it down, write them in respectively. Next one is to divide by their AR. Okay, so this one they did not provide the relative atomic mass for each of them, so you have to refer to the periodic table. Okay, if you refer, you can see that C, carbon, is actually 12. Am I right? Okay, which will give us 0.3. Hydrogen is actually just 1, so it's 0.6 divided by 1 give us 0.1. Same thing. Whereas for oxygen, okay, it's actually 16. So 4.8 divided by 16 to give us 0.3. Okay, so now we have to divide by smallest, that was step 3. So which one is the smallest here? We can see that 0.3, 0.6, 0.3. So 0.3 has to be the smallest. Okay, so everybody divide by 0.3. So 0.3 divided by 0.3 gives us 1. H, 0.6 divided by 0.3, because it's the smallest, give us 2. 0.3 just divide by 0.3, which is itself 1. Okay, so this is the same as previous example, except that now we don't have to multiply it to a whole number because it's already in a whole number. But say that this is 1.5, then we have to do the next step, okay, which is times 2, times 2, times 2, etc. But since this is whole number, we can just ignore the fourth step. Okay, so now we have found out the empirical formula, which is CH, alright, CH2O. Why? Is because the ratio of C to H to O is written here actually. 1:2:1. Okay, so C1, H2O1. Okay, but I skip the 1 because we don't write the subscript for 1. So empirical formula is just CH2O. From this one, okay, so I can ignore all this step above already. I can just focus on this guy. Okay, CH2O. Okay, the relative molecular mass, MR, of this molecular formula, we can now calculate it. Okay, it's actually 12 plus 2, okay, sorry, not 2, 1, because it's H, but there are 2 H's now, so 1 times 2, plus 16. Okay, to give us a nice number of 30. Okay, so now we have both the MR of EF and the MR of MF. And remember that N, the N that we want to solve, it's this one here, right? Okay, just a recap. MR of MF over MR of EF. Okay, so maybe I just write it here for your reference sake. MR of MF over MR of EF. Okay, so this is the formula that we can use. So to find N, we just plug the first number. Top number is MF, right? 180 here. Okay, 180 over the bottom number, which is 30, the one we just found, to give us a nice number of 6. And so we can see that MF is 6 times of EF. What do I mean by this step? Remember this one? Okay, so my MF is 6 times of EF. Okay, that's how you get the number n, right? Okay, and that's why my molecular formula is now C6, okay, H12O6. Why? It's because previously my empirical formula is this guy, am I right? CH2O. But now it becomes C6H12O because all this number here, 1, 2, and 1 times 6 individually. Okay, because they are a multiple of 6. Okay, so everybody just times 6 here, and I will get C6H12O6. Okay, maybe I just do a quick summary of this molecular formula because it's a bit confusing. Okay, the first 3 steps I think is quite clear cut. Okay, first one, mass, you just plug in whatever is being given. Second step, you just plug in whatever is given on top. Okay, the numerator. Denominator is just AR. Okay, divided by AR, sorry. That means individually, what's their AR? Okay, C is 12, H is 1, O is 16, etc. Next step is to divide by the smallest. So we can see that 0.3 is the smallest, just divide individually. And then we get 1:2:1. That's the ratio of C is to H is to O. And then we can know our empirical formula is CH2O because it's C, H2, and O. Make sense? And okay, so after when we get this one, CH2O, we can ignore this whole chunk here. We can just throw it out. Okay, we just focus on here now. And we can see that CH2O has the molecular mass, relative molecular mass of 12 plus 1 times 2 plus 16, because based on just this formula to get 30. And then use this formula, 180, to divide by whatever we've gotten, 30, to get 6. And we know that it's 6 times of MF, 6 times of EF, sorry, and that's why we just times 6 to everybody here to get us C6H12O6. Okay, this is a bit hard to digest at first, but once with more practice, okay, you'll be able to get it. Okay, and that'll be all for empirical and molecular mass. Molecular formula, I mean, sorry.